In this video, we're going to cover section 2.4 on resonance. Now, resonance is a method that chemists use to deal with the inadequacy of bond line drawings. And we draw resonance structures, which are a series of structures that are melded together conceptually to circumvent the inadequacies of bond line drawings. So you can see in this particular example, we have a 3-carbon system, carbocation located at one of those positions, and a pi bond between the other 2 carbons. Now we can redraw this particular intermediate as shown. And in actuality, this system is coexisting between these 2 forms, these 2 bond line structures. And so we use this double-headed arrow to represent that these are hybrid structures of one another. So the 2-headed arrow and brackets indicate to you that these drawings are resonance structures of one particular entity or one particular molecule. And this one entity is called a resonance hybrid. So let's look at this example in a bit more detail. So this 3-carbon system is known as the allyl cation. And what the resonance structures are aiming to show you is that this positive charge is actually spread out between these carbons in this particular entity, this molecule. So we can draw this carbocation in one of 2 ways. We can have the carbocation, the electron deficient carbon center located at this position, or in the other structure at this position. And so both of these resonance hybrids represent that single entity. And so we show them by redrawing the various possibilities for that particular entity. So the spreading of charge, the spreading of this carbocation throughout this 3-carbon system, or you can think of it as the movement of these pi electrons from being between these 2 carbons to these 2 carbons, this is known as delocalization. So delocalization is referred to as a stabilizing factor, that whether it's the movement of a positive charge or a negative charge, the ability for that entity, for that molecule to delocalize that charge over not just a single atom, but over a few atoms, stabilizes the molecule. And this stabilization is often referred to as resonance stabilization. And so we would say that the allyl cation is resonance stabilized. We can use curved arrows in our resonance structures to show us how we get from one resonance hybrid to the other. And so the curved arrow formalism, which we'll spend more time discussing when looking at reactions between molecules, is also used to describe the movement of pi electrons or non-bonding pairs of electrons in resonance structures. So I can start my curved arrow from the pi bond and direct the head of that arrow to the sigma bond, which connects the electron deficient carbon center, the carbocation, with the single carbon in the middle. And so as you can see, the result of that movement of pi electrons places those pi electrons now between these 2 carbons. And as a result of that movement, this carbon center now is electron deficient. And so it would carry the formal charge of +1. Similarly, we could also use a curved arrow to show how we could go from the right side, the right-hand structure, back to our original structure on the left. One last point to mention is that when we draw our resonance hybrids, it's important to contain them within a set of square brackets. When we see this set of square brackets, it indicates to us that the structures within those brackets are the resonance hybrids for one particular entity and not for multiple molecules. So that is something that is important to remember when drawing resonance structures, is that A, you incorporate them in a set of square brackets, and the type of arrow is very key. The type of arrow is a double-headed arrow, and it's only used to indicate one resonance structure from another. So those are two important aspects to remember when drawing your resonance structures. Now, a few other points to make about drawing curved arrows for resonance structures is that we avoid breaking single bonds. So as you can see in this first example, this would not be considered a resonance structure. These are two different chemical entities. What's happened here is you've broken a bond as opposed to delocalized electron density within 2 or 3 atoms. And so this would be an incorrect resonance structure and not something that you can do with your curved arrow formalism. A second rule to follow when drawing resonance structures is to never exceed the octet for second row elements, which basically states that when we draw our resonance form, we should never have more than 8 electrons around a particular atom from the second row. And so, for example, if we were to draw what we would possibly perceive as a possible resonance structure for this example, we would end up with the following. And you can see quite clearly that either oxygen has more than 8 electrons in its vicinity. So we have 3 lone pairs and 2 bonds, and so here we would have 10 electrons around this particular oxygen and 10 electrons formed in non-bonding pairs and bonding pairs with this oxygen. And so we violate the octet rule as a result, and so this would not be considered a resonance form. So there are basically 5 patterns for drawing resonance structures shown in this figure. And the first is the little lone pair, where we have a 3 atom system. So here we have a lone pair on this oxygen, an additional lone pair than oxygen would normally have in its neutral state, neighboring a carbon that's bound to another carbon via a pi bond. And so in this example, if we were to use these 2 curved arrows and to draw our resonance structure resulting from it, we would end up with the following. And I'll include the lone pairs just so that we can keep track of it for our discussion. And so what happens here is we have the migration of one of these lone pairs on oxygen. It will become a new pi bond between the oxygen and the carbon, and that's shown here. But in order to not violate the octet rule, we have to use a second arrow to move the pi bond, the electrons in this pi bond, to a new orbital onto this carbon atom. And so that's what's shown below, is that we have formed a new pi bond from an original lone pair, and we've broken a pi bond to give us a new lone pair, a carbanion, on this carbon. And so this would be considered the 2 resonance structures, and I'll draw in my square brackets around it. These would be the 2 resonance hybrids representing this particular entity. So that negative charge is really delocalized between this oxygen and carbon-carbon system. So this carbon-carbon oxygen system, this negative charge, you can consider it being delocalized between those 3 atoms, and as a result, you have a more stable entity as a result. If we look at the second example, here we have a carbocation as we saw in our previous example. So again, no surprise, the result of this would be, again, the movement of the pi electrons from those 2 carbons on the left, if you will, to those on the right. And so that's going to leave an electron deficient carbon. So again, these would be the 2 resonance structures to describe this particular entity. So a third example of a pattern for drawing resonance structures is when a lone pair is adjacent to a positive charge. So in this example, we have a carbocation center and a neighboring element, oxygen, which contains 2 lone pairs. So we can redraw this particular resonance structure as another hybrid to represent this entity in the following way. In doing so, the formal charges are going to change, of course. And so now oxygen will take on that formal charge of +1. But the carbon to which the electrons were moving towards, it now is satisfied with its tetravalent system. And again, we would draw we would draw square brackets around those 2 structures. A fourth example is when a pi bond is between 2 atoms of different electronegativity. So we could draw a curved arrow as shown to represent the movement of electrons in that pi bond between the carbon and oxygen towards the more electronegative element, oxygen. And so the resulting structure would be the following. And now we go from a system that was neutral to one that has both a formal charge of -1 on the oxygen and +1 on the carbon. I forgot my double-headed arrow. There we go. Throw it in there. And then finally, we have a fifth pattern, which is observed with systems, ring systems like these, which are called aromatic systems. This is benzene, where we just have the movement of pi electrons around the ring. And so we can show what's known as conjugated pi bonds in various resonance forms. So this will look very similar to the structure above, but just the placement of the pi bonds within the ring would be altered. And so this would be considered a resonance form of that original conjugated pi system. So in summary, these are the 5 patterns for drawing resonance structures. And what's key to remember is that when we use curved arrows to move electrons, whether they be bonding pairs found in pi bonds or non-bonding pairs found on hydrogen atoms like oxygen and nitrogen, we're simply spreading that electron density through the structure. And so we use resonance structures to depict that, because on their own, an individual resonance form doesn't describe the full picture of what that entity looks like in reality. And so that is one of the inadequacies of the bond line drawings, is that they're static, whereas the resonance structures allows you to see how dynamic the structure is in terms of the delocalization of charge, whether that is a positive charge being delocalized in our allyl cation system, or the movement of a negative charge through a system. So let's look at a couple examples by completing the following resonance structures. And we'll add our curved arrows to each structure to show the electron movement. So in this first example, we see we have a carbocation center, and neighboring this carbocation center is an atom that contains a lone pair. And so that should indicate to you that that is a potential source of electron density in the drawing of a new resonance form. So let's first draw in our curved arrow to represent the electron movement, and then redraw our new resonance form. Again, we're going to use a double-headed arrow to represent that that is in fact what we're doing. And because this lone pair was used to form this new pi bond, that's going to change the formal charge of this nitrogen center from 0 or neutral to a +1. And finally, we used our square brackets to indicate that these two structures represent a single entity. And again, we can use our curved arrow on the newly drawn structure to show that electron flow that would get back to our original resonance structure. Now, if we look at the structure below, here we have a pi system, that of the carbon double bond oxygen, neighboring an anion or a carbanion center. And so again, we could take these electrons, we could show the delocalization of this additional charge by moving these electrons to form a new pi bond, which would then require the breaking of that carbon-oxygen pi bond so that we don't violate the octet rule for the second row element, carbon. So we can draw a curved arrow from the lone pair and direct the head of that arrow directly at that sigma bond. But we can't stop with a single arrow. We need to use an additional arrow to show the movement of the pi electrons from the pi bond between carbon and oxygen to that oxygen center. So again, we use our double-headed arrow to represent that this is a resonance form. And we redraw our structure. And I'll explicitly show the lone pairs. And we'll have to provide oxygen now with its correct formal charge, which now changes from the neutral state, formal charge of 0, to now formal charge of -1. And again, we would use our square brackets to represent that these are resonance structures for a single entity. And we could similarly show the curved arrows to represent, again, the movement of those electrons within the structure. So there are two examples of resonance structures for particular molecules. And if you have any questions about resonance, by all means, send me an email or start a discussion in our forum. Thank you.